Today, we're diving into a story that stretches across a century, one that connects a deathbed mathematical mystery to the very fabric of our quantum reality. How could a ghost from the past end up haunting the future of physics? Well, let's find out. On the surface, these two ideas could not be further apart. You've got this flash of pure, abstract insight from a dying genius, and then you have this cold, hard physics problem about a bizarre theoretical universe. And yet, somehow, they're two sides of the exact same coin. So, let's start at the beginning. Our story doesn't kick off in a high-tech physics lab, but with a letter. A final, cryptic message that would puzzle mathematicians for decades to come.
Seriously, try to picture this. It's 1920. One of the most brilliant minds in history, Srinivasa Ramanujan, has only months to live. And he's not reflecting on his life. No, he is furiously scribbling down brand new mathematical functions, ideas that seem to come from absolutely nowhere, with almost zero explanation. He knew he'd found something, and he had to share it before it was too late. He called them Mach theta functions. Now, the best way to think of them is like these beautiful, incredibly intricate patterns that have this ghost-like quality. They almost follow a perfect set of rules, but not quite. It's like they're the shadow of some deeper, more complete mathematical object that no one could actually see. And for nearly 100 years, they just remain this tantalizing enigma.
So what are these things even made of? Well, at their very core are these building blocks called Q-series. And you can think of a Q-series as a highly sophisticated, kind of secret code for counting things, for arranging them into patterns, sorting them, and understanding their deep structure.
Look, we're not going to get lost in the formula here, but the crucial point is this. A Q-series is the fundamental language. It's like the DNA of Ramanujan's mystery functions. But here's the kicker. This language of counting and arranging isn't just for abstract math. It's the exact same language physicists use for something called a partition function, which is their tool for counting all the possible states in a physical system. And trust me, that connection, it's about to become very, very important.
Okay, let's hit the pause button on 1920s mathematics. We're going to jump forward a whole century and leap straight into the strange world of theoretical physics, to a place I like to call the quantum donut.
So yeah, we're trading the pen and paper for particles and probability waves. The question we're asking is no longer, what is this strange function, but how does a single particle behave in a very, very strange universe?
So, welcome to the torus. And yeah, it's a universe literally shaped like a donut. It has no edges. If you're a particle living on this surface and you travel in any direction, you don't hit a wall. You just loop right around and end up back where you started. It's a perfectly contained, endlessly repeating reality. Pretty weird, right?
Now, life on this donut has some really specific rules. Because the space repeats, the particle's momentum can't just be anything. It becomes quantized, which means it's restricted to specific, discrete values. And the particle itself isn't some tiny ball, it's more like a wave that's spread across the whole surface. Kind of like a complex musical chord made up of lots of fundamental notes all playing at once. And this is where you really see that quantum weirdness in action. The particle's position is a smooth, continuous wave, but its momentum, where it's going, is choppy, restricted to these exact integer-based steps. It can have 1 unit of momentum or 2, but it can never have 1.5. So, how do we make sense of that complex wave chord? Well, we use a nifty mathematical tool called a Fourier transform to break it all down into its fundamental notes. And each of those notes corresponds to one of those allowed quantized momentum states. It is the perfect language for describing our particle on the donut.
So, we've got Ramanujan's mysterious counting functions from 1920, and we have a modern quantum physics problem. Now let's build the bridge and reveal one of the most beautiful and totally unexpected connections in science.
Here's the central challenge the physicists were facing. They needed a way to count and organize all of the possible states, all those possible musical notes their particle could have on the torus. They needed, in other words, a partition function.
And this is the absolutely mind-blowing part. The physicists needed a tool for counting states. And it turns out, the perfect tool for the job already existed. Ramanujan's Mach theta functions, yep, those ghost-like patterns from his deathbed letter, built from Q-series, are precisely the partition functions needed to describe the quantum donut. The answer to a 21st century physics problem was just waiting, and a 100-year-old mathematical riddle.
So why is this so useful? It's because Ramanujan's work is a masterclass in what's called asymptotic behavior. It gives physicists an incredibly powerful shortcut. Instead of calculating every single state one by one, they can use his formulas to instantly understand how the system behaves at extreme energies or temperatures.
And I gotta stress, this isn't just some cute mathematical curiosity. This connection is fundamental to modern physics. It helps us understand how quantum states grow in complex systems, it's a key ingredient in string theory, and, get this, it even helps us calculate the entropy of black holes. Ramanujan's ghost is literally haunting the frontiers of physics.
This unexpected bridge between two completely different worlds really forces us to ask a much deeper, almost philosophical question about the nature of reality itself.
What's so fascinating is that even within physics, there are different mathematical languages to describe the same reality. In one view, the particle's wave changes over time. In another, the wave is fixed, but its momentum evolves. They look completely different, yet they give the exact same answers. They're just two languages describing one physical truth.
And that brings us to our final question. The story of Ramanujan and the quantum torus is a stunning example of this. Was the structure of quantum mechanics somehow encoded in pure mathematics a century before it was even needed? Or is math just such a powerful and flexible language that we were bound to find a dialect that could describe the universe perfectly? You know, we don't have the answer, but the connection itself is a profound hint about the deep and mysterious order of our world.